Okay, well, thank you very much for being back here after the short coffee break. And thank you to the organizers for organizing that. It's the second time I'm attending one of these meetings, and I really enjoy it always. So I thought I should say something about Bohmian mechanics. And actually, it's not obvious from the title, and also not from the early part of my presentation, but actually there is something related to Bohmian mechanics. As you see here, and I'm going to use this screen maybe because actually it's only the guy sitting there that gets to see the pointer. I guess no one can see the pointer here anyway. Maybe I move from one to the other side so that the chairman is happy with me. Okay, but so here you clearly see this beautiful clock which I have in my office. I should take a video that you can see that it's indeed running and it indicates time usually. And it's made on purpose to be quite regular. It's a clock, so it should be non-chaotic. And also in quantum mechanics, we have this unitary transformation, so this big rotation in this huge Hilbert space, which is also one of these very regular and very boring deterministic evolutions. So this is really the typical deterministic evolutions. But we know that in physics, and especially maybe in quantum physics, we also have a typical non-deterministic evolution. For instance, if you send a photon on a beam splitter and put two detectors, you get a random event. And you may name one detector 0, the other one a 1, and then you get a string of random bits. And you can even make that commercial. You may buy one if you like. And actually, you don't need to buy one. Just a little information for the fun of it. You may download this app. It's for free from App Store or wherever. And provided you have a modern smartphone, so that is not going to work for Roddick. I don't know where Roddick is, but for Roddick it will not work. But for most of you, I'm sure it works. And this will turn your smartphone into an elementary quantum processor, producing truly quantum random number generator. So you actually have a quantum processor in your pocket, except Roddick. And so this is fun. And so we believe that actually quantum physics is non-deterministic. And there are good reasons for believing that. Actually, we heard already quite a lot about that. You can use two of these random devices. And provided we also have now inputs, outputs we always have. And assuming that distance really exists. So there's really a distance between here and the end of the room, and between Geneva and London and so on. Distance exists. And assuming that there is no hyper-deterministic conspiracy, or no super-deterministic conspiracy, as we also already heard the first day, and assuming, but the last one is something you can measure, that you get some promise about the relations between the inputs and the outputs, then you can violate the famous CHSH inequality. And depending on the amount of violation you get, and depending whether you are just in a quantum regime or in the superquantum with these PR boxes, you get some randomness. So randomness is really something that comes out of these very, very mild assumptions. Distance exists, no deterministic conspiracy, and the observation that you get that with a high enough probability, then you get this randomness. And just by the way, as probably all of you know, Bohmian mechanics avoids this randomness by denying the existence of distances, since things or influences or the quantum potential can jump from here to there, whatever distance, in no time. So distance does not really exist. So that makes physicists, and especially quantum physicists, extremely convinced that quantum mechanics is non-deterministic. So our world is not deterministic, the universe is open, and you can publish nice papers. But what about classical mechanics? So we all learned that classical mechanics is, on the contrary, deterministic, because Newton's and Maxwell's equations are deterministic, giving some initial condition. The future, and by the way also the past, can in principle be computed. Actually, just maybe again a side remark for the fun, if you have some very special dome called here the Norton dome, which has exactly this shape here, then there is something funny that can happen. You can throw a ball up roll the ball up the dome, and if you throw it gently enough, it will not reach the top, but just come back. If you throw it too strongly, it will go over the top and go down on the other side. But if you throw it with exactly the good velocity, initial velocity, it will, in a finite time, stop exactly on the top and stay there. But Newton's equation is time reversible. So consequently, if you now start from a ball sitting on the top of this Norton dome, it can, according to Newton's equation, start at any random time, any random direction, and move away spontaneously without violating Newton's equation. So maybe Newton's equations are not that deterministic after all. But this is a very contrived example, so I think it's funny, but it's maybe not as deep as it may look, because you need really to have very, very precisely this kind of shape in order to avoid the well-known theorems that tell you that Newton plus initial condition, Newton equation plus initial condition guarantees a single solution. But now let's look at a chaotic classical system. Let's assume, okay, just here a number between 0 and 1. We stretch it, so multiply it by 2, and then everything that is above 1 we put back by subtracting 1. So the function that we are looking here is multiplying by 2, so 2x, and then if it is larger, if 2x is larger than 1 or x is larger than 1/2, you subtract 1. Now if we write x in a binary form, we have the bits here, x1, x2, x3 are bits, and clearly, so if x1 is equal to 1, then we are on the right-hand side. If x1 is equal to 0, we are on the left-hand side, and so on. And then if we look at the effect of this map, it is just shifting. So every bit gets shifted to the left by 1 unit, and the first one is dropped, moves away. Okay, a very simple evolution. It looks perfectly deterministic. Okay, as I said, now whether x lies on the left half or the right half after n steps depends on the nth bit, x index n, of the initial condition. Very simple. Let's keep that in mind. Yeah, we can then even make it a bit more practical. Say, okay, on the left it means it's a sunny day, on the right-hand side it's a rainy day, and here we're not in London, it's 50-50. Okay, now let's look and consider these initial conditions that we have both in Newton's equations, in this little toy example, or also in quantum mechanics or in Bohmian mechanics. Everywhere we have real numbers. Now let's consider a finite region of space, this cubic millimeter, whatever it is. And the assumption I want here to put forward is that in a finite volume, you cannot have more than a finite number of bits. So a finite volume of space cannot contain infinitely many bits of information. I think this is a kind of assumption you buy or you don't buy, you like it or not, but it's very natural, especially today where information theory and quantum information theory is extremely popular. So we count everything in bits, and in a finite volume you cannot have more than finitely many bits. But that means that now if I have a classical ball inside a volume, classical object inside my finite volume, the position of the center of mass of that object cannot be a real number, because a real number contains infinitely many bits. So actually, why do we call these numbers real? It's because of Descartes, who wanted to distinguish them from the imaginary ones, or the complex ones, as we would say today. But it's certainly not because Descartes called real or named real the so-called real numbers that they are really real. And really, in my opinion, the idea that real numbers are truly real are ontologically real is absurd, because the single number could contain an infinite number of bits, as already said. But for instance, in only one real number, one could code the answers to all questions one could possibly formulate in any human language, as Gregor Chatin, among others, emphasized. So a real number is something like a monster, and there is no reason to believe that this has a real physical existence. So mathematical real numbers are not physically real. So what are the consequences of that? Let's look back to this example here. So now if the initial condition x is not physically real, it might be given by a real number, but it's not really physically real, maybe it's only a rational or a number that can be computed, then if we agree that this billionth bit of the initial condition has no physical existence, whether x points to the sunny or to the rainy after a billion of steps is not predetermined, but is truly random. So we see that even if the map, this map here, is deterministic, if the initial condition it cannot be described by a real number, because real numbers have no reality or no ontological reality, then actually the evolution is random. Even more, most of the, or almost all real numbers are uncomputable. You have only countable many software programs, so you have, consequently, most of real numbers are not computable. And so if we would, a better name for the so-called real numbers is actually a random number. Because really the digits of a real number are really as random as what comes out of a quantum random number generator. Take a singlet, you measure half of it, you get a you get a random number out, which is of quantum origin. But actually take a real number and look at the next digit, it is exactly as random. It's totally random. So you have randomness also there. And indeed, we should call them, so we should really call them random numbers. This doesn't mean that we should now forget everything about real numbers. Real numbers are still extremely useful to do our theory. So no way to throw that away. But it is only an idealization. So real numbers are actually random numbers. Mathematical real numbers are physical random numbers. And so if at school we would all have learned to name these numbers random numbers instead of naming them real numbers, which in a history fiction could really happen, we would probably not be so convinced that classical physics is deterministic, because we would not base determinism on random numbers. But it so happened that in our history, we name them real numbers. And maybe here one of the first conclusions here I like to emphasize is that whether Newtonian classical mechanics is deterministic or not is not really a scientific question. We'll never be able to really measure anywhere a real number. It's really a matter of faith. So you may say it's maybe not science, it's faith, or it's beliefs, or it's, you may like it or not, or you depend also on the kind of ontology you like. I'll come back to that. And it's certainly not because the model or the equations we have of nature are deterministic that nature herself is deterministic. And this was emphasized nicely by Elisabeth Anscombe, who wrote, "The high success of Newton's astronomy was in a way an intellectual disaster. It produced an illusion, for this gave the impression that we have here an ideal of scientific explanation, whereas the truth was, it was the mere obligateness on the part of the solar system by having had such a peaceful history in recorded time to provide such a model. So it happens that the solar system, at least over the last millions, maybe even billions of years, was like the clocks I had at the very beginning. And we were lucky with that. Of course, without that, we wouldn't be here to talk about it. But most of the systems, the classical dynamical systems, are chaotic. So what is non-determinism? So if you try to define that, there's something, okay, it's random, it's unexpected, unpredictable. So for instance, here I have a card. It's upside down. You don't know what it is. And now comes a surprise. This is the card. So this was, of course, unpredictable to you, or at least to most of you, but it's not the first time I used that slide, so some of you knew it already. So it was unpredictable, but for whom? Well, the true randomness should be unpredictable for everyone. Should be intrinsically unpredictable. If you look on Wikipedia, it's a lack of pattern of predictability in events. Now, if you think also, mathematicians, we have a kind of different definition. We think in terms of complexity or Kolmogorov complexity, possibility to compress the information. And so for mathematicians, actually randomness is about a given sequence of bits, so eternal bits. They're given at once forever. But for a physicist, we are more thinking in terms of dynamical events, things that happen, like the output of a quantum random number generator, or like the weather of tomorrow. Tomorrow there will be, well, sunny or rainy, but tomorrow will be, and so it's a dynamical event. So it's a very different view between the physicists and the mathematicians here. And of course, predictability refers to the future, well, most of the time. And so clearly predictability and randomness, hence, is connected to time. Okay, so now so far what I tried to convey as a plausible statement is that physics, whether it is classical or quantum, is non-deterministic. So what can you do once you face this situation of non-deterministic physics? And I guess there are essentially two possibilities. One is to look for supplementary variables such that this randomness is no longer intrinsic but becomes purely epistemic. By ignoring this supplementary variable, you get actually the randomness. That is certainly one way of proceeding. A second one is to accept the idea that besides the res extensa, Descartes' res extensa, you really have res potentia, so potentialities or dispositions or propensities, to use Popper's terminology. So let's first look at the first alternative, to look for supplementary variables. And there are several possibilities there. And one possibility is to add additional universes, the many worlds kind of stuff. And important is really to realize that these additional universes are intrinsically not accessible. You cannot gain information about what is happening there. But that is one possible path. A second possible path, very natural for this conference, is to supplement quantum with point particles, let's say Bormian positions. And again here, these additional positions, these supplementary variables, are intrinsically inaccessible in the sense that it is impossible to gain information about them beyond that they are distributed according to psi square, or the square of the absolute value of the wave function. If not, one could signal. But you can do that, and this is certainly an interesting path. And a third possibility is to supplement Newton's mechanics with real numbers, with the mathematical real numbers. And by the way, these additional digits that you would then postulate to classical Newtonian mechanics are equally inaccessible. And now, I guess people, well, let's say the Bohmians, not so many as I expected in this audience, they would maybe be happy here because essentially what I'm saying is that if you accept real numbers in classical mechanics, which essentially 99.999% of the physicists do, then for exactly the same reason that you accept real numbers for classical mechanics, you should accept Bohmian positions in quantum mechanics. It's the same kind of step. It's a very natural step. And vice versa, if you refuse the Bohmian particles or the Bohmian mechanics, well, you should also refuse real numbers in Newtonian mechanics. The second possibility, when we face non-determinism, that means
5 for you.
5.
And then 5 questions.
Yeah, okay, so it's 10 altogether. Good. So the second possibility when you face non-determinism in physics is this, to accept res potentia. And we're not really used to that. That's why maybe I think it's very interesting. We're not really used to the idea that potentialities really truly exist, especially not in physics. We have plenty of other, okay, in human science, we are full of that. Now, the real challenge, if we accept res potentia, is to find out when these potentialities become actual. You know, so today, tomorrow's weather is not predetermined. But tomorrow there will be either rain or sun. So at some time, these potentialities that tomorrow will be a sunny day will have to turn actual. When is that going to happen? Well, this is actually the well-known quantum measurement problem. Now, if we follow the path that I'm suggesting, namely that real numbers are actually random numbers, physically non-real numbers, then in Newton mechanics, we also have a measurement problem. Let's call it the classical measurement problem. It's actually the same problem as we have in quantum. And I think as soon as we accept res potentia, we have a measurement problem, or we have a problem which maybe we should remove the word measurement because it probably has nothing to do with measurement and human beings. We just have the question, when does potentialities turn into actualities? So according to scientific determinism, everything that happens today is the ineluctable and necessary consequence of some possibly quantum fluctuation in the initial state of the universe. I'm not exactly sure what this means, but essentially it means that, you know, given something far away in the past, or by the way, far away in the future, if we have scientific determinism, everything that I'm saying, that you're hearing or not listening or checking your email, whatever, was already determined by this initial fluctuation in the initial condition. So time is an illusion. It is merely an evolution parameter that labels the necessary unfolding of some initial state. And here is really where I probably diverge from, let's say, the Bohmians, in the sense that I don't believe at all in determinism. I also, by the way, will diverge completely from the many worlds. I just think determinism is a déformation professionnelle. I don't know how you say that in English, but you know, physicists, they get kind of screwed by their, well, profession, and because we learned about equations and all these beautiful clocks and solar systems and things like that, at the end we start believing in determinism. But it is absurd. There's no reason at all to believe in determinism. So we live in an open universe with creative time and events. So I come to the conclusions. And so the main one is that the mathematical real numbers are physical random numbers. And in particular, that whether Newton classical mechanics is deterministic or not is actually not a scientific question that just science is going to answer for you. You have to believe or not in it, or maybe I should not say faith here, maybe I should have said philosophy. Because you can argue in favor, you can very rationally argue in favor of one or the other, but it's not just science that is going to give you the answer. It's not experimental science. Now, adding supplementary variables to quantum and classical physics is a logical possibility, though the fact that these additional variables are not accessible, you cannot really gain information about them, makes their status debatable. Again, if you have a real number, and I give you the first billionth of digit, that provides you exactly 0 information about the billion plus 1 digit, the next digit. So they still are inaccessible in this sense. You can't get any information about what is beyond. So accepting, on the other side, accepting res potentia, as I find very attractive, because one doesn't need to add these ad hoc and inaccessible supplementary variables. However, then we have this question, when do potentialities become actual? And yeah, we should not focus only on the quantum measurement problem. We have the same problem actually in classical mechanics. Thank you very much.